Dr. Mazur is the Balkansky Professor of Physics and Applied Physics at Harvard University and the Area Dean of Applied Physics. An internationally recognized scientist and researcher, he leads a vigorous research program in optical physics and supervises one of the largest research groups in the physics department at Harvard University. Now, when I was in the Air Force, I was looking for something to do at night, so I registered for a graduate physics course in optics. Boy, was that dumb. It was a lot of work. It's not what I envisioned, and no pun intended. Dr. Mazur has made important contributions to spectroscopy, light scattering, the interaction of ultra-short laser pulses with materials, and nanophotonics. In addition to his work in optical physics, Dr. Mazur is interested in education, science policy, outreach, and the public perception of science. He believes that better science education for all, not just science majors, is vital for continued scientific progress. To this end, Dr. Mazur devotes part of his research group's effort to education research and finding verifiable ways to improve science education. In 1990, he began developing peer instruction. Peer instruction is a method for teaching large lecture classes interactively. His teaching method has developed a large following, both nationally and internationally, and has been adopted across many science disciplines. Dr. Mazur has served on numerous committees and councils, including advisory and visiting committees for the National Science Foundation, has chaired and organized national and international science conferences, and presented for the Presidential Committee of Advisors on Science and Technology. He serves as a consultant to industry in the electronics and telecommunications industry. He is chairman of the Instructional Strategy Advisory Group for Turning Technologies, a company developing interactive responses for the education market. He also serves on the scientific advisory panels for Allied Minds, a pre-seed investment company creating partnerships with key universities to fund corporate spin-outs in early-stage technology companies, and on the scientific advisory board for the Lifeboat Foundation, a nonprofit, non-governmental organization dedicated to encouraging scientific advancements. He is the author or co-author of 236 scientific publications and holds 12 patents. He has also written on education and is the author of Peer Instruction, a user's manual, a 1997 Prentice Hall book that explains how to teach large lecture classes interactively. In 2006, he helped produce the award-winning DVD titled Interactive Teaching. And of course, he also finds time to do some actual classroom teaching. So please welcome Dr. Eric Mazur and his talk titled Confessions of a...
Wow, there are a lot of you here. I guess you must all like public confessions. It's kind of intimidating, you know, to be confessing in front of so many people. I'd rather be doing this one-on-one. I guess I just have to remind myself of the American proverb, the more you confess, the more books you will sell. So let's get started. Here's my first confession. When I started teaching at Harvard, that was in longer than I want to admit, 1984, I never asked myself the question, how am I going to teach? The question didn't even come up in my mind. To me, it was quite obvious what I was going to do. I was going to do to my students what my teachers had done to me. I think it's sort of a natural assumption that we all tend to make. We tend to project our own experiences onto the world around us. After all, we learned it in a classroom setting, not very different from this one. So I think it's kind of natural to assume that everybody learns that way and becomes successful in their fields. In retrospect, it's a strange thing, right? When you start doing something new, the first question you should ask yourself is, how am I going to do it? But anyway, question didn't come up in my mind. I stepped in front of the classroom without any training, and I started teaching the way I had been taught. And to make matters worse, within a couple of years, all the signs were that I was a successful teacher. I was doing the right thing. What are the traditional standards by which we assess education? Well, one is the dreaded end of semester questionnaire, which I'm sure you have here too, the evaluation. As an assistant professor at Harvard, I was asked to teach the course that, I didn't know that at the time, I just gladly accepted my teaching assignment, but that none of my colleagues wanted to teach, namely physics for pre-medical students. These were not students who were taking physics because they wanted to learn physics, not at all, they'd heard nothing but horror stories about it. They had to take it in order to satisfy the pre-medical requirement. And these pre-medical students were generally not very kind to my colleagues when it came time to evaluate the course at the end of the semester, but not so for me. I got 4.2, 4.5 on a 5-point scale. So clearly the students liked what I was doing in front of the class. So that's one metric. Another metric is the student's performance on exams. Typically when, in this country at least, when physics is taught to pre-medical students, it is reduced to algebra level. There's no calculus in it. Well, not so at Harvard. At Harvard, we give the pre-medical students a full-blown calculus-based course. I could ask these students some questions involving triple integrals that I wasn't sure I could do under the pressure of time. But by and large, my students did well. So in short, they did well on what I consider to be complicated exam questions, and they gave me high evaluations. Of course, I was doing the right thing. Now, in retrospect, there were always some disturbing signs under the surface, but I ignored them, right? If there are positive signs and negative signs, so why pay attention to the negative ones, right? I'm an optimist. I only look at the positive things. You know, each year, in spite of giving me high ratings, some students would write in the comment section at the bottom of their end of semester evaluation, "Physics is boring," or "Physics sucks." I could never make any sense out of these remarks, so I ignored them. Same thing when I go to a party and people ask me what I do for a living. You know, "Oh, you're a physicist." I had such a hard time with physics in high school or in college. And it always creates a feeling of embarrassment. And I never used to understand why physics education causes so much frustration among people. Recently, I was at my dentist, and I couldn't even speak back because I had the thing in my mouth, you know. And he said, "Oh, you're a physicist." Well, I got an A in college, for physics in college, but I really didn't understand anything. Anyway, I could never make any sense out of these remarks, so I simply ignored them and focused on the positive aspects and happily went on lecturing in front of the classroom. That all sort of came to a crashing halt when, in 1990, I read a series of articles that was published in the American Journal of Physics. Let me pause for a moment on that word physics, because I'm a physicist. We might have 1 or 2 or 3 physicists in the audience, but most of you will probably not be physicists. I do not want to create the impression that this talk is about physics. It's about education and about pedagogy. However, I'm a physicist and I want to use a couple of examples, so they'll be from physics. But if you're a chemist or if you're an engineer, mentally substitute the word chemistry or engineering each time you hear me say the word physics, because I'm quite sure that the message of my talk applies just as much to your discipline as to my own. Okay, but I will use a few examples from physics. Anyway, back to this article in the American Journal of Physics, published by David Hestenes, a professor at Arizona State University. And in that article, actually it's a series of articles, he published a survey, a questionnaire if you want, called the Force Concept Inventory, FCI. How many of you have heard of the FCI? Few people. Okay. So the FCI is a conceptual survey that tests students' understanding of the concept of force, as the title suggests. Now, let me tell you a little bit about typical curriculum in physics. Week 1, you start with discussing motion. Week 2, you describe the concept of force and connect motion to forces. And the framework for discussing forces are Newton's 3 laws. Then in subsequent weeks, everything builds on top of those concepts. If you do not understand forces, the rest of physics simply does not make any sense. Let me give you an example out of this force concept inventory, or FCI, and I'm going to give you the question that turns out to be one of the hardest on this test. Okay, are you ready? A heavy truck and a light car collide head-on on the highway. The force exerted by the heavy truck on the light car is A, larger than that of the light car on the heavy truck. B, the two forces are equal in magnitude to each other. C, the light car exerts a larger force on the heavy truck than the other way around. D, they're not exerting any force on each other. They are just in each other's way. Now you're laughing about that. I think no physicist in his right mind would ever come up with such a crazy answer. The way Hestinus developed this FCI was not by sitting at his computer typing in answers. The way he developed it was by giving it as free response questions to the students and tabulating the most frequent incorrect mistakes. And I think, answers, I mean. And I think that's the only correct way to actually develop a multiple choice test. If you know the right answer, it's very difficult to come up with plausible wrong answer because your mind doesn't work like that of a beginning learner. So I never believed in multiple choice tests, but if you actually put in the effort to collect student responses, you can make a valuable multiple choice test. Because if you have this wrong mental model, trucks and cars don't exert forces on each other because forces only occur in physics courses, not in the real world, then you know, it actually will distract the student from the real answer, and it'll become a powerful way of testing their preconceived notions about these concepts. Well, in spite of the fact that most students who've taken a physics course have no trouble reciting Newton's third law. Newton's third law tells, you may have heard of it, action is reaction. The force of A on B is equal in magnitude to the force of B on A. Even though they have no trouble reciting that law, when A and B get replaced with truck and small car, Newton's third law all of a sudden doesn't apply anymore. Now, the interesting thing is that this force concept inventory does not use any physics jargon. Yes, it has the word force in it and acceleration and so on, but you don't need to have taken physics to have a certain mental concept of what these things mean. So you can give the FCI as a pre-test at the beginning of the semester and then repeat it at the end of the semester to see how much students have learned. It's a way of measuring the learning gain due to instruction. And what Hestinus claimed in the article was that students gain precious little. There's very little difference between the post-test and the pre-test. And he showed some data which were absolutely abysmal, showing that most students were still Aristotelian thinkers, back to the ancient Greek, at the end of their physics course. And he tested 5,000 students in Arizona, New Mexico, California. So, I mean, this was statistically very significant. I first looked at that. I learned Newton's laws in high school. So I thought, you know, and most of the students in my class at Harvard have a 5 on the AP-B and AP-C exam, the advanced placement exam. So I thought, you know, the only reason that I am doing a quick discussion of forces is a review. I mean, they've all learned it in high school. This has nothing to do with what I'm doing in my class. But then Hestinus showed that the evaluation of the professor had very little to do with the gain. In other words, whether it was an award-winning teacher or just an average teacher, you got the same gain between pre-test and post-test. In fact, it doesn't matter what we do in front of the students, the gain is low. Well, I read that and I thought, just no way. Not my students. Not Harvard students. After all, you know, this was all in the southwest of the US. Maybe it was some disease that was raging in that part of the country. In the northeast, we surely were much better. Unfortunately, it was too late to administer a pre-test because it was November, so we were already 2 months into the course. We were dealing with rotational dynamics. Students had to calculate moments of inertia by integrating over the volume of complicated object. I mean, we were so way beyond Newtonian mechanics, or at least the Newton's laws, that the test had very little connection to what we were doing in the class at that time. But I was dying to show that my students would ace this FCI. So one day I walked into the classroom and I said, look, I'm going to give you a quiz. I didn't want to call it a test because, you know, pre-meds, when you say the word test, they freak out, right? And I said, look, you don't have to worry about this quiz at all because it's not going to affect your final grade in any way. I'm just giving it to you to assess the effectiveness of my own teaching. And as I said that, I realized I'd just taken away any incentive for these pre-meds to even participate in the quiz, right? I mean, if you tell a pre-med this is not going to affect your final grade, he or she won't even show up. So I thought I better give them a reason to come. And I said, look, next week we have a midterm coming up. The midterm dealt with rotations, parallel access theorem, you name it. It was, you know, quite complicated. I said, we have a midterm coming on. If you take this quiz seriously, it will help you pinpoint where you might have difficulties, and you may improve your performance on the midterm. As soon as I said that, I realized I was telling them a huge lie, right? And I was worried that when they would see this FCI, this quiz, they would be offended by the simplicity of this test and accuse me of wasting their time with something completely, you know, trivial. Oh boy, were my worries quickly dispelled, because hardly had they started taking the test or one student raised her hand and she said, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? I stood there, you know, I just had no idea how to answer that question. And by the time the test had been completed, I had been dragged out of my ivory tower, and it literally was a turning point in my teaching career. Anyway, what I'd like to sort of get across in this opening talk, and I hope you will keep it in mind in the coming day and a half, is that we should really shift the focus from teaching to helping students learn. If I look at this message now, it looks to me to be completely trivial. I add some meat to it. And I'll do that in three parts. First, I want to talk a little bit about education. And then, because presumably we're all involved in education, but if you stop to think about it, if you try to actually define what education exactly is, I think many of us would actually struggle to write down a concise and accurate definition of the concept of education. We all know what we mean by the word, but articulating what education is actually not so simple, which is sort of ironic, right? How can you be engaged in education if you can't define what it is? So that's why I want to talk a little bit about education. Then I'll talk about peer instruction, which I developed in response to discovering how little my students learned. I'll show you some data in just a second. And lastly, I'll show you results. And I want to pause there for a moment because I think it is crucially important that in our approach to teaching, we display the same scholarly rigor as we display in our own research. I don't see a big difference between what I do in the classroom and what I do in my laboratory. Yes, I collect data in both cases, and they're very different. In one case, it's the interaction of light with matter. In the other case, it's the interaction of words with students. But in both cases, I can use the same rigorous approach in order to try to improve the goals of what I'm trying to do. In one case, it's understanding nature. In the other case, it's advancing learning and advancing the development of skills in the students I teach. And I think it's very important to collect data and to have the same type of approach as we have in the classroom in terms of developing a hypothesis, obtaining data, making modifications to your approach and then see if the data improves or not. If it does improve, then you keep that approach. If it doesn't, you modify something else. Because too much of what we do in education is dictated by anecdotes. When I go to a faculty meeting in my own department and the discussion turns to education, it's just amazing how people rely on anecdotal evidence rather than on data. So what I'm going to actually show you is data to back up what I'm saying. For those of you who have to contend with colleagues who rely on anecdotal data, let me give you a nice little quote from Lee Shulman, former president of the Carnegie Foundation. He said at one point, "The plural of anecdote is not data." In other words, you don't validate an argument just by giving a lot of anecdote. We need data. So for that reason, I'm going to show you data in this talk. So let's start by discussing education. What do we mean by education? Step into any classroom, including this one right here, right now, and you're likely to see a scene that's very similar to this picture, which was taken in my classroom in the late 80s, early 90s. I would like you to describe to me the activity that is taking place on the screen there. And the words, and preferably I would like to have a short description. Please no 5-minute discussions. Just a short description, preferably using a verb. And the verbs I don't want to hear are teaching and learning because I'm not 100% sure what they mean. So how would you characterize the activity that is taking place on the screen right there? Listening. Listening is what would describe only the part that the students are engaged in, right? Pointing at something, but now we're talking only about what I am doing in front of the classroom. Lecturing. Lecturing is actually, there's quite an irony in that term, lecturing. The word or the verb to lecture is derived from the Latin verb for to read. In fact, one of the ranks of professors in the UK is called a reader, right? Well, there's a certain irony in that. I'll tell you a little anecdote about my own classroom in just a minute because there's some reading. But again, we're sticking to either describing what I'm doing or what the students are doing. Let's find a sort of more comprehensive way. Communicating. Professing, we're back to me, right? Observing the students.
Trying to absorb.
Trying to absorb. Absorb what?
Right.
Knowledge, I hear here, but what is knowledge? I would probably characterize it as follows. What's happening here is transfer of information, delivery of information. And you know what? The students had rubbed this in my face, and I had ignored it. Let's go back to the beginning of my talk. I told you I never asked myself, how am I going to teach? What do you think the question was that came up in my mind when I was asked to teach this pre-med course? It was not how am I going to teach, it was what? What textbook am I going to? So I went to a colleague and he said, oh, for this course in the past we've used Halliday and Resnick, a classic physics textbook still used to this date. And it had already been used 20 years before I taught this course. So I went to the Coop, the Harvard Coop, which is the bookstore, and ordered 150 copies of Halliday and Resnick. And as I walked back from the Harvard Coop, from the bookstore to my office, I asked myself, wait a minute, if all the students have this book, what do I do? You know, in Leiden, in the Netherlands, where I did my undergraduate and graduate work, you would never buy a book for a classroom because, I mean, why would you buy a book if the professor was presenting the material out of the book? There was not, I came from a culture where, except for graduate courses, you didn't buy books. So instead of going to my office, I went to my colleague's office and I posed that question. And he said, oh, don't worry, there are plenty of introductory physics textbooks. And he showed me his collection on the shelf. So I started looking, and very quickly there was one book which I really liked for two reasons. One, it had a slightly different approach. Rather than starting from Newtonian mechanics, it started with conservation of momentum. The other reason was actually much more important. It was out of print. Students couldn't get their hands on this book. It was my, secret book to teach from. So for each lecture, I prepared a set of lecture notes. I took a chapter out of this other book, Widener and Sells, and turned it into 10 pages of lecture notes. And in the classroom, I would either project the notes on the overhead projector or would write it on the blackboard. Now, because the development and the notes were slightly different from the textbook, I thought it'd be good for my students to have a copy of my lecture notes. So as they would walk out of the classroom, on the back side, the side pointing towards you, at the top I had stacks of photocopied lecture notes so they could pick one up on the way out. Why do you think I handed them out at the end of class and not at the beginning? I didn't want them to just grab the notes and go back to bed. But in retrospect, isn't that already admitting that there's something wrong? Why force them to come and listen to me if they can get the same information, if they think they can get the same information out of the notes? That question never came up in my mind, but anyway. So students loved my notes because they were much more concise than the 30, 40 pages per chapter in the textbook. But after a few weeks, some student came to me and they said, Professor Mazur, couldn't we get a copy of your lecture notes at the beginning of each classroom? This way we don't have to write down that much. And I indeed noticed that each time my chalk went A on the blackboard, 150 pens went A in the notebooks of the students. I once heard somebody describe the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. Well, that's precisely what was happening in my classroom. I was taking all this time to take the information out of Widener and Sells, turn it into my textbook, into my lecture notes, and then the lecture notes would be either written on the board or on the overhead projector. Students would put it in their notebooks, but the information, the place where the information really needed to get, the brains of the students didn't get there. Anyway, so I thought, okay, I'll hand it out at the beginning of each classroom. And much to my relief, students wouldn't just grab the notes and go back home. No, they grabbed the notes, sat down, and they still copied everything because they had no time to read the notes. So it didn't actually make that much of a difference. Now, the next year that I was teaching that same course, I said to myself, you know what? Rather than handing out these lecture notes class by class, a week before classes start, I'm going to take the collected set of notes for the entire semester, send it out for duplication, and on day one, students get the entire package for the whole semester. You know what the unexpected result was? The unexpected result was that about half a dozen students wrote in the comment section on the end of semester evaluation, Professor Mazur lectures straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I handed out? I was livid. These ungrateful students. But they had a point. I was lecturing from my lecture notes. I was just focusing on transferring information. And had they looked at the textbook, even their own, they would have seen that the information in there was not that different from the one I transferred. So, as you see, students had pointed out and I had ignored it. So let's ask ourselves now the following question. Is that what education is? Is education merely the transfer of information, or is there more to it? Who agrees with the statement? Lectures, delivery of information. I see a few people say, yes, that's it. There's nothing else. So let's first take that hypothesis. I'm really surprised because generally I have nobody in the audience who thinks that's true. I would disagree with that statement too. But let's assume it's merely the delivery of information. That would be really bad because that means we're all going to lose our jobs very quickly. Because if it is just the delivery of information, then why do we have to reenact this delivery year after year after year? It's a one-way flow of information. I know that because if I lecture, and I love lecturing, which is why I'm so happy that I get to lecture to you here today, I know that because if I stop and I say, does anybody have a question? Good. Yes? I'm very serious. This is very serious matter. I'm trying to make you laugh, but I am serious.
What's the fellow in the background back by the blackboards doing in the classroom?
That was actually one of my teaching assistants.
What's his purpose in there?
Her. She was actually, this was when we had a total, we're on a sidetrack here, but after I started developing interactive teaching, we wanted to have a technology-based solution for collecting responses. So at that time we had wired calculators. This was the pre-clicker era. This was probably one of the oldest clicker systems ever in use. There's one older one which dates from Cornell from the 60s, where a physicist, high-energy physicist, had doorbells in the 3 doorbells, 1, 2, 3. It was an analog system, and the more students pressed a certain doorbell, there had 3 analog meters in the front. So you got this. That's the oldest clicker system. This is the second oldest clicker system in the world. So she's actually behind a computer station that's underneath that surface there, looking at the responses. So this was actually not really a lecture, but it was already in a transition period to an interactive lecture. But let's go back to, if education were just the information transfer, then all we need to do is just videotape some good lectures. We could break it up. Why force the students to come and listen to a professor if they don't ask any questions anyway? And why make these lectures an hour and a half long? Cut them up into 7-minute bits and have them watch it on their iPod. You don't lose anything. If you have a question, you can still ask it, except the professor's not there, but in the classroom, nobody uses that opportunity anyway. And you can have the students look at it whenever they want to look at it. So I think if education is just information transfer, then we're in trouble, universities. We really need to change things right away. But I don't believe that. I think there's a very crucial, and I saw only a few people shake yes. So I want to hear from the people who did not shake yes. What is it that is missing?
You asked the question, I think, what do we think lecturing is? Now, you didn't ask what do we think lecturing should be.
No, I said, what do I think education is? Did I say lecture? Oh, I am sorry. I meant education. I must not have slept enough. I am sorry about that. I meant what is education, not what is lecture. So is education merely the header there? Is education merely the transfer of information? So what is missing? Knowledge, experience, learning. I mean, these are all other words that I think, just like education, are really hard to pinpoint. Problem-solving strategies, applications.
Generalization, incorporation.
Generalization, incorporation. This is very close to the way I would have formulated it.
We have to motivate them to do what they got to do to learn.
We have to motivate them, but I would argue that the lecture can be actually very motivational. In fact, I'm here lecturing you to motivate you for interactive pedagogies, and I hope I will be succeeding in doing that without having clickers and other things. But let's get back to what we just heard here. I think the hard part of education is not this delivery of information. It's the fact that the learner has to do something with that information. You have to assimilate that information. You have to internalize it. You have to build mental models that you can apply in a situation that you've not seen before. And that hard part of education has to happen in the brains, in the minds of the students. Where did that happen for us, who all became professors? Think back of your own education. Where did you internalize the information? Where did you build the mental models? Where did you take ownership of the information that was transferred to you? Did it happen in the classroom while you were taking notes, listening to the professor? I don't think so. You had your hand up.
I had a pretty strict dad. He gave me a book. Told me to go to my room, and
So you learn on your own.
that's how you do it.
That's how you do it.
I learned it when I started teaching it.
Thank you so much for saying that. We'll get back to that later on, but I think that's true probably for a lot of us. In fact, I know that on occasion I have taken on the teaching of a specific course because I wanted to learn it.
Obviously, for many of us, it's the homework, but that's the using of...
The homework, again, is, you know, and there we are on our own struggling with the material. So I think the actual learning, the hardest part of education is not taking place in the classroom. It's taking place outside of the classroom. It's sort of ironic that we put all of our effort in the easy part, the information transfer, leaving the hard part to the student. Okay, so that education is not just information transfer. It became clear when I started to give this FCI. So here's the FCI pre-test on the first day of class when I was still teaching a totally traditional course in 1990. And there are 29 questions, which is why the scale ends at 29 here. When I took the test, I got 28 out of 29. I must have misread a question or something like that. No, I made a real mistake. I wanted my students at the end of the class to be in the last 3 bins. Okay? When I as a physicist saw that test, I thought, okay, they can make no more than 3 mistakes. That's how simple I thought the FCI was. Hestenes says that anybody who scores below 23 is still an Aristotelian thinker, still connects force to velocity rather than force to acceleration, as Newton's second law stipulates. If you put a monkey behind the keyboard randomly pressing buttons, you'd get something like 10, or, you know, because there are about 3 answers for some questions. So you can see that some Harvard students, in spite of having taken an AP course, score barely better than a primate. It's very scary when they score lower than that. And believe me, it happens. This year I had a student who scored 4 out of 30 on the pre-test and only 7 out of 30 on the post-test. I wasn't teaching the mechanics part. I inherited that students in my E&M course. Anyway, so you see 2/3 of the students score below that cutoff of 23, but you know, I haven't taught them yet, so let's see what happens after 1 semester of award-winning teaching by yours truly. Not much. At least there's a gain. But if you put the 2 distributions on top of each other, you see that there's still, first of all, a really large fraction scoring below 23. And, you know, we may have moved some students from the lower end to the high end, but not nearly what I wanted. Let's plot it slightly differently. Let's take these 2 distributions and take the averages. On the horizontal scale, we put the pre-test average, class average score, which is 70%. And on the vertical scale, we put the change in the score. They went from 70% class average to 78, so the gain is 8. What could the gain have been? Well, if you're 70, you can go to 100, so it could have been 30. A perfect post-test score would give a point on that diagonal line, right? So the closer we are to the diagonal line, the better. And as you can see, my data point is not too close to the diagonal line. Why do I plot it this way? Because this allows me to compare to totally different schools, from community colleges on the far left to large state schools in the middle to some liberal arts colleges, and then one lone point on the far right side, which is my class at Harvard. Notice that the community college students on the left gain substantially more than my Harvard students. They have a 20% gain. See that? Of course, they start out much, much lower. They start at 30-something or 20-something. So they end lower than where my Harvard students start. But notice something interesting. There's a trend in these data points. I can draw a line through them, meaning that regardless of the academic setting, in a traditional lecture format, students gain only about a quarter of what they could, and I would say should, gain. Right? At Harvard, 8, where they could have gained 30, about a quarter. And the community college, 20, where they could have gained close to 80, and in between. So universally, the lecture method does not appear to work very well, whether it's a selective institution or a two-year institution or you name it. So it's not the transfer, but the assimilation that is key, and unfortunately little assimilation is happening in a traditional format. Now, when I saw the results that I just showed to you, it was a shock. And the first thing that I thought, well, Eric, maybe you're not such a good teacher after all. But that could obviously not be true, right? So, I just disregarded that very quickly. So what's another possible explanation of the poor result? Dumb students. But, at Harvard, that's sort of hard to claim. So I thought about it a little bit more, and then I came up with the perfect excuse. Put yourself, because we're always trying to find excuses, right? Put yourself in my position, right? You're convinced you're a good teacher, you're giving this test, and you get this horrible result. What do you think my twisted brain came up with? Huh? Wow, you must have heard my talk before. Exactly. Usually you have to pull on an audience to get it out. The test, there had to be something wrong with this test. Think of it. Heavy truck, light car colliding. You don't have to take physics in order to know that you're probably better off, or that the collision is going to have less effect on the motion of the truck than that of the car. So I thought maybe students are confusing acceleration or damage with the magnitude of the force. Maybe it's just, semantics rather than real understanding. After all, if I gave them a problem involving the force of 1 on 2 or A on B, there was no problem with doing Newton's third law. None. So I decided to do some testing of my own. And that's when I discovered another very serious problem we're facing in education, namely that the way we assess our students paints a very misleading picture. We give information to them in the classroom. We expected them to parrot it back. And the way we assess it allows them just to parrot information back, making us believe and them believe that there's actually learning that has been taking place, but it's not. So I'm going to give you one example. This is a little bit of physics. It will appeal probably to the electrical engineering folks and the physicists in here. If you don't understand the physics behind it, don't worry, because it's not about the physics, it's about the idea. What I decided to do was to put two problems on exactly the same subject, electrical circuits, but one in turn was a standard textbook problem and the other was a word-based problem. Here's the standard textbook problem, was lifted out of a textbook. You have two loops, and these wiggly lines here are resistors, and the values of the resistors are given, and two batteries, an 8-volt battery and a 12-volt battery. And the students were asked to calculate the current in the 2-ohm resistor and the potential difference between the points P and Q. We could all take a piece of paper here, at least those of us who know about DC circuits, and take 10 minutes to work out the problem. And I'm sure that if we'd compare our answers, we'd find a whole range of answers, and many of us, including myself, would probably made a mistake somewhere, a minus sign, a factor 2, whatever. The point I want to make is there is ample opportunity to make mistakes in solving this problem. So this was problem number 5 out of 5 on a midterm examination. On that same midterm examination, I put this problem. 3 identical light bulbs, A, B, and C, are wired in series, like the light bulbs in a Christmas tree, to a battery. And then there's the switch S here, which shorts out, don't try this at home tonight, it's dangerous, okay? Which shorts out the final light bulb C. When you short something out, all of the current goes through the short. Right? It has no resistance that passes, so all of the current goes through, nothing goes through the light bulb anymore. And the students were asked the following questions. When that switch S is closed, what happens to the intensity of light bulbs A and B? And the only thing the students had to say was it increases, decreases, or stays the same. I didn't want any calculations. I even told them it's not necessary to motivate the answer. Just tell me if it increases, decreases, or stays the same. Now, in retrospect, I should have asked for their reasoning, because that's important, but I didn't that year. What is the intensity of light bulb C? Or no, what happens to the intensity of light bulb C? What happens to the current through the battery? What happens to the potential difference across the 3 light bulbs? And what happens to the total power dissipated? If you understand DC circuits, it takes 30 seconds to answer this question. And of those 30 seconds, you spend probably 25 on part E. That's the hardest part. The rest you just answer. Well, what I didn't tell you is that when we teach large courses, and in that year there were about 200 students in the classroom at Harvard, 2 professors share the teaching of that course. We alternate 1 week, one professor, 1 week the other, and the professor who doesn't teach can interact with the students. So in order to put this on the exam, I had to convince my colleague that this was a good exam problem. So I gave him a handwritten draft, and he looked at it, and he said, "Eric, you're out of your mind." And I said, "No, I don't think so." He had not been part of the fall semester, so I told him about the FCI, and he listened patiently and then said, "But Eric, we only have 5 problems on this midterm examination. We cannot give away 20% of the exam." And I said, "Give away? I hope we're giving it away, but I'm not sure." I'd been the one teaching DC circuits, so I thought it was my prerogative to decide how we would assess the students. Well, I had to argue with him for half an hour, and finally he reluctantly agreed to put this on the exam. And we made it problem number 1, the warm-up problem. Well, it turns out students overheated on this problem. Professor Mazur said one student, this problem number 1 was the hardest problem on the exam. Or another student who said, I didn't know how to get started on this problem. What do you mean getting started? If you're started, you're done, right? It's just it's a one-step thing. Well, I decided I would grade this problem. Remember, I'd asked the students just to write down increase, decrease, stay the same. So I thought that in an hour and a half I could grade 200 exams because I just quickly had to see increase, decrease. Big mistake. It took me an entire weekend, 2 days. These pre-meds had freaked out on this problem. Some had written 6 pages in their blue book, in their examination book, writing down everything they knew about DC circuits in hope of somehow writing the right thing. For the electrical engineers among you, some were talking about RC times in this problem. I mean, it was just amazing. And when I had finished grading, it was clear that we had a problem. On the left, you see the score, a histogram of scores out of 10 for the conventional problem, and the average was about 7 out of 10. On the right, you see a similar histogram for the conceptual problem, and you see it's 5 out of 10. Same subjects, same students, same day. Do you see that huge peak at 2 right here? Right here? That's about half the students. Well, some had written down so much that I was able to reconstruct their thinking, and it turned out that 50% of my students had made the same basic assumption. When the switch S is closed, this is just to entertain the engineers and physicists in the audience, and I promise this will be the last physics I show, okay? But I can't resist because it's so funny. When the switch S is closed, nothing happens to the current through light bulbs A and B. After all, the current hasn't yet arrived at the switch. So, right? I mean, how can it know? Just it arrives there at this junction just as it did before. When the switch is open, the current can only go straight. When the switch is closed, it gets a choice, right? Going straight or taking a right turn. So the big question is how much of the current is going to take a right turn and how much of the current is going to go straight. What do you think 50% of Harvard students assumed? 50-50. Of course, it all goes through the switch, but 50-50. One half takes the right turn, the other half. Okay, so what does that do to the answers? Well, nothing changes in A and B. That would be the first. So in A, they would say stays the same. That's wrong, because when the switch is closed, you only have 2 light bulbs connected rather than 3, and 2 have less resistance than 3, so there's more current through it. So they got that wrong. What about answer number B? Well, B gets half the current, so therefore the intensity goes down. So what did they write down? Decreases. You know what? That's where they got their 2 points. The light bulb goes out, but I had to be fair and give them their 2 points. These are pre-meds. Some are going to be later surgeons who do bypass surgery. Anyway, I said same students, same day, so let's look at the correlation. Well, here they are, the data point. There's not much correlation. So for each data point is a student or several students on top of one another, and I show the conceptual problem score on the vertical, the conventional problem score on the horizontal. Now, but if you're willing to stretch your definition of a line a little bit, you find that about 52% does equally well at the top here, or equally poorly on both types of problem. But now look around it. 40% of the students lies below that. There's even 6 students who get full score on the conventional problem, but they're not even able to get their free 2 points. Now look on the other hand. Well, this 40% makes sense, right? Doing well on the conventional, but not that well on the conceptual. But now look here. This is empty. It's white. There are no data points. Saying that a student who understands the concepts gets the traditional problem right as well. But let's focus for a moment on these 40%. Who are these 40%? What are these students? Why are they there? How would you classify these students? They want to pass? They all want to pass.
Plug and chugger.
They're Harvard pre-meds.
Plug and chugger.
Plug and chug. They solve the problems by rote. They follow a recipe. And we can't blame the students because, you know, you open any textbook and somewhere on page 20 there's this box that says problem-solving strategy. You know, read the problem, make a sketch, choose your act. You know what I mean, right? Now imagine you're a pre-med. You've heard nothing but horror stories about physics. You know that your physics grade is important because whether or not you're going to get into Johns Hopkins depends on your physics scores. They're used as a filter. Now, in the week 1, you see this box that says problem-solving strategy. You think, my key to success. You pull out your yellow highlighter and you highlight this entire section. It's already been highlighted by the publisher, but you highlight it anyway. And you memorize the recipe. Now comes problem set number 1, homework. Problem number 1, and here is the recipe, pardon me, strategy. And you apply the strategy to the problem. And you know what? It works. Why does it work? Because most of our textbook problems are written so as to match the procedure or strategy or whatever you want to call it. And you think, hey, maybe physics is not going to be that bad after all, and I'm going to get into Johns Hopkins, and you get excited. And then you apply it to problem number 2, and it works again. And then you apply it to problem number 3, and it works again. And, you know, I could never understand, as I told you in the beginning, that students would think of physics as being boring. But if it's just applying recipes, it is boring. You're throwing out the baby with the bathwater. It's just, especially if you don't understand why the recipe works or doesn't work. Now comes number 4. Problem, recipe, you try, it doesn't work. Why? Because as we know, not all problems are solvable by strategies. In fact, I would argue, if there is a problem-solving strategy for solving a problem, you don't have a problem anymore, right? It's just applying the strategy. So here you are, you can solve 3 problems but not 4. You get frustrated, especially because you don't understand why. And on the exam, let's talk about these students on the exam. Go back to the times that you were a student, right? It's the day of an exam, you've been cramming hard, you've studied, you're sitting, leaving one space between you and your neighbors. The professor and the teaching fellows are handing out the exam. It's with the printed side down. You're sharpening your pencils. You're quickly looking through your notes to get that last bit of information into your brain. And at some point, the professor says, put your books away. You may now begin. Everybody turns silent. Remember those moments? Yeah? And you can hear 150 exams being turned around at the same time. And as you turn the exam around, your eyes see this picture. This picture. Right? You turn it around and within 500 milliseconds you see that picture. What is the first thought that crosses your mind? Very specific here. Kirchhoffs laws, exactly, because Kirchhoffs laws are the laws that describe how currents distribute themselves in things. You haven't even read the text, but you know already, because you've been pre-programmed. If you see a diagram with wiggly lines, that means a Kirchhoffs Law problem. Right? So then the exam falls onto its back. You haven't read anything yet. You're a second into the exam, and you already know problem number 5 is a Kirchhoffs Law problem. And then how much physics is left once you've made that identification? Hardly any, right? You just take the numbers out of the figure and plug them in the right spot in Kirchhoffs Law, turn the crank, and out comes the answer. Now, did the students understand Kirchhoffs Law? Well, there's a reason I'm showing this. No, because if they understood Kirchhoffs Law, they would have had no problem with this. Anyway, so when I realized that, that was the time that I finally asked myself the question, what should I do? And the first thing I thought was, well, maybe I should teach graduate courses. But I wasn't willing to give up that quickly. And it turned out that the solution presented itself serendipitously. I told you I was afraid that the students would be offended by the simplicity of this FCI. They weren't offended at all. They were very worried that they had done so poorly. So they asked me to make a session, to have an extra session where it goes through every question on the FCI. When we got to this question of the heavy truck and the light car, I made a free body diagram for the light car on one side of the board, another one for the heavy truck. I drew the forces on each, and then I said by Newton's third law, the force of the light car on the heavy truck is equal in magnitude to the force of the heavy truck on the light car. What more is there to explain about it? I turned around, and I could at once see from their faces that they were very confused about this. So I said, does anybody have a question? They were so confused they couldn't articulate a question. You know how it is, right? If you're really confused about something, it's hard to actually articulate that confusion. So there are two things I could do, just go on, right, because there were no questions, but I knew this was serious, so I thought, okay, you know what, I'm going to redo it and bring in acceleration. I'm going to argue that in spite of these two forces being equal, the effect on each of those two objects are going to be very different because one is light and the other is heavy, and so they're going to have different accelerations, and they can have different accelerations even when they're stuck together because, well, I don't want to teach you physics here, but anyway, my explanation was just brilliant. And I turned around triumphantly knowing I'd nailed the subject, only to see that they were even more confused. I had no idea how to explain it better. But I knew one thing. I knew that about half of them had given the right answer. So I thought, why don't I have them just discuss it? So I said, why don't you discuss it with your neighbor? And something happened that I'd never seen before. The entire classroom erupted in chaos. They forgot about me in front of the class. And what was more, within 2 minutes, they figured it out. I was really shocked by that at first. I thought, why are they doing such a good job explaining to one another and I can't? But the reason is simple. Imagine you have Mary and John sitting next to each other. Mary has the right answer because she understands it. John does not. On average, Mary is more likely to convince John than the other way around, right? Force of reasoning. But this is the key point. Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it and still has a feeling for the conceptual difficulties that John has. Whereas Professor Mazur learned it such a long time ago, he has no idea what the difficulties are that are going on in John's mind. It's sort of ironic. You'd say the more of an expert you become, the more qualified you are to teach it. In a sense, I'm arguing the contrary. I'm saying, the more expert you become, the harder it becomes to teach it. Anyway, I decided I'd do that, exploit that in my classroom. And if we think of education as a two-step process, information transfer followed by assimilation, then why not throw all of the information transfer out of the classroom and then use the in-classroom time to help the students assimilate the material? So now I either have the students watch a video of a lecture out before coming to class, or I have them read the notes before coming to class. And in class, I teach by questioning rather than by telling. I go into depths rather than covering everything. The coverage is essentially determined by the pre-class component in the reading. And I do the questioning through concept test, which gave rise to this whole clicker craze that is going around the globe right now. And a concept test basically has the following steps. I begin by asking a question. I may have a brief presentation, a question. Then I give the students some time to think about this question. I have them commit to an individual answer. Then I tell them, try to find a neighbor who has a different answer and convince that neighbor of your answer. And I have them recommit to an answer. So there's commitment, discussion with peers, followed by another commitment to a new answer. And then I have an explanation which depends on how well they do. And then the cycle repeats over and over again. So let's see in a little video how this works in practice. Displaced in a uniform magnetic field in the direction indicated by these arrows. So the question is, what are the magnetic forces on the 4 different sides of this loop? So I read the question with them to make sure that they all understand the question. They think, I don't want them to talk to each other. Often they get very eager to talk. Your answers. We have a disagreement clearly here. So turn to your neighbor and see if you can convince one another of the correct choice. Aha moment there. Initially we had sort of an even split, and now we have an absolutely overwhelming majority for choice number 2. It's not unusual to go from, let's say, 40% correct answers to 90%. Right? If you have too few correct answers, the question doesn't work because there are not enough students to teach other students. If there are a large number of initially correct answers, like 80, then the improvement is not that great either, and a lot of discussions are not very fruitful. So the important thing is to aim sort of for an initial percentage between, let's say, 30 and 70%. So what is happening here? Well, 2 things. One is it's active, not passive. You can't sleep through class. Every few minutes your neighbor will start talking to you. Believe it or not, some students complain about that. They'd rather be sleeping than talking to their neighbors. The other thing is that there's now a 2-way flow of information. It's not just from me to them, it's from them to me. I don't have to wait till the exam to find out whether or not they understand something. I see it right then and there on the screen. And even after using this method for many years, I'm still being surprised by the performance of my students sometimes, which is usually a negative surprise rather than a positive surprise. The other thing is that there's feedback to the students themselves. They get to continually assess their own knowledge. And I don't know if you saw this article in Science, which was also carried by a number of newspapers like the New York Times, that showed that frequent testing through a process known retrieval reconsolidation actually improves the learning. I was really happy to see that. This was in the January 21 issue of Science, to see that there's actually a real cognitive, I would even say neurological basis that supports this approach to teaching. It's a very interesting article, and we can talk about it later if you want, because there are some potential barriers to implementation too that are clear from this article. But anyway, as a student, you can see where you stand with respect to your peers. And if you don't understand something, you don't have to wait till the problem set or the midterm examination to find out that you didn't understand it. It is continuously, brought out to you. So let me, in the last few minutes, answer this question. Is it any good? Well, let's first use the FCI and see how they did on the FCI. 1991, FCI pretest. Among all the data I have collected in my career, both in the lab as well as in the classroom, these are the most reproducible data. It's just amazing. Probably says more about the admissions office than about me as a teacher, but it's very interesting to see how stable that it was in one. The noise, of course, is different, but it was in 1 or 2 percentage points they're the same. Now, when people show data, they often say these are some typical data, where typical is a code word for these are the best data I've ever obtained in my entire career. Well, I'm going to show you some atypical data because I'm going to show you the data from the first year of implementing peer instruction. I was still groping in the dark. I didn't know what the right questions were to ask in class. But even in the very first year, look at the post distribution. Significantly better. Not all in the last 3 bins, but certainly the upper bins are the most populous one. And yes, there are still some students who are Aristotelian thinkers, but it's substantially less than before. Did I teach to the test? I made sure that during the year there was not a single question that I asked on the homework or anywhere else or in class that came close to one of the questions on the FCI. I didn't want to, influence that result. In fact, in 1991, I was so excited by these results, I submitted an abstract to the American Association of Physics Teachers summer meeting. Nobody knew about me in education, so all I got was a contributor talk. I flew out to Vancouver, and they're 8-minute talks, believe it or not. I don't know how you can get anything across in 8 minutes. But anyway, I spent 4 of my precious 8 minutes documenting that I had not taught to the test. I didn't want anybody to accuse me and say, yeah, well, no wonder your results are better because you went over these questions. At the end of my talk, somebody raised his hand and said, don't worry about teaching to the test. We've tried it. It doesn't work. Anyway, so where's the data point on this plot now? Instead of an 8% gain, I got a 16% gain. And in subsequent years, it actually tripled rather than just doubling, simply by a better selection of the questions to ask in class. And the highest data point was obtained by 2 of my colleagues when I was in sabbatical. So it's not dependent on instructor either. And other schools that have implemented this interactive type of teaching have also obtained substantially larger gain. If you don't focus just on the best data but take them all together, you see that implementing interactive teaching doubles the gain on this FCI. But the FCI is just what we do in the beginning of the term. What about real problem solving? I knew my colleagues would ask me this question. So how do you test that? Well, what I decided to do was to do something I'd never ever done, to repeat an exam. I had never ever repeated a single exam question. At Harvard, we keep 3 years of exam on file in the library. Any student who had looked at it would have seen that all my exams were different. And even if somebody had had access to all 7 years, that student would have very quickly concluded Professor Mazur never repeats an exam. But I'd meticulously kept data, so I could go back all the way to 1985 and replot this histogram. And I said to myself, look, if I get this again in 1991, as long as the performance doesn't slide too much, why did I prepare myself for it sliding a little bit? Because I had done no problem solving in class. I decided in 1991 that students derive no benefit from seeing me with my back to them solving a problem on the board and then copying the solution in their board. The only way, imagine you want to learn to play the piano. You don't learn the piano by putting in CDs of Murray Pariah playing Chopin sonatas and listening to them. You got to play. You don't train for a marathon by sitting on the couch in front of the TV eating popcorn watching DVDs of marathon runners. You got to do the running. You don't learn physics problem solving by watching a Harvard physics professor solve problems. You got to do the problem solving. So yes, we had problem solving, but it was all outside of the classroom. But anyway, you know what? In 1991, they did better, even though we had done less problem solving in class. Statistically significantly better. The gain is maybe not as large. It went from, I think, 60% average or something like that to 68% average, 10%, less than the gain in the FCI, but still a very statistically significant gain. So what does this mean? This means that better understanding leads to better problem solving. But, and I think this is the most important message I want to really get across to you today. If you take the inverse of this statement, it's not true. Good problem solving doesn't always indicate understanding. I've been fooling myself into believing that I was a good teacher based on the performance of my students on examination, but it was just a house of cards, right? It was just memorization by rote, and the real underlying understanding was not there. I had a little video about what the students have to say of it. I'm going to skip that. I'm going to skip out of it. And wrap up here with 2 comments. One is the traditional indicators of success in teaching, I think, are very misleading. The end of semester questionnaire got high ratings, students learned next to nothing, and also a lot of our assessment is actually paints a picture that is not accurate, that does not really tell how much we're learning. And secondly, I think education is no longer about information. And one of the ways I've tried to act on that, I mean, information comes out of everywhere right now, right? So what I do now is that I tell my students that on the exams they can bring whatever they want. Books, laptops, smartphones, whatever they want. They cannot bring another person, another living person, dead person. Okay. But they can bring whatever they want because, you know, when I do my work and when they're going to do their work later, they have access to that information. It's not about memorizing the information, it's about knowing how to use the information. And the memorization has to come not from cramming, but from using it over and over again. Right? If you look something up many times, eventually it'll just stick. And it'll stick because you form a mental model of it. Now, since I did that, this has been the laptops is fairly new because I never knew whether or not to allow laptops because what if students are going to start messaging each other? Well, there's no time. They can message about the answer, but I look at the solution, not just at the answer. So fine if they message. I don't care too much about it. But what has the effect been? The effect has been two things. One is that I'm telling students very forcefully it's not about memorizing information anymore. But secondly, and this has had a much bigger impact, I think, is that I discovered that a large part of the questions that I used to ask on exams are meaningless because they can simply be copied out of the textbook or from the web. I've had to work much harder on making a meaningful assessment, one that will assess the type of skills we really want our students to develop, regardless of, you know, the setting and the discipline. So with that, I'd like to thank those. This is the wrong final slide. Doesn't matter. I'm just going to go here. I want to acknowledge the National Science Foundation. If you want a copy of this talk, you can go to that URL. Thank you so much for your attention. You want to?
Years ago, are you still doing that?
Absolutely.
Points on the concept question when they come into class and you read the material.
So the questions about the reading before, do I give them points for that? Yes, I do give them points. There's actually, in order to get them to prepare themselves in a meaningful way for class, I do two things. I have a carrot and a stick. The points are the stick. The reading assignments are worth 10% of the course grade, and you cannot make up for it any other way. So in other words, if they don't do the reading, they don't earn these reading points, they'll go from 100 points to 90 points. They basically drop an entire letter grade. This is not how I present it to them. I say, look, by working consistently, you can earn 10% of the grade. You have to spin it positively to the students, of course. But in essence, it's a stick because they lose a significant credit. And I tell them, look, it's not important that you answer the questions correctly. What matters is that you convince me you've done the reading. So they'll put in a lot of effort trying to convince you that they've done the reading. And it turns out it's really easy to evaluate that, much more easily than to evaluate whether an answer is correct or not. You can actually fly through it and say whether or not the effort has been. The carrot is this, is that the third question is always the same. The third question, which is not content-based, is please tell us what you found difficult or confusing in the reading. If you did not find anything difficult or confusing, tell us what you found most interesting. So the day before class, I press on a button, and out rolls the names of the students with their faces and what they found confusing. I will answer some of these points of confusion directly via email. We've built in an FAQ system that allows me to very quickly process those responses. But more importantly, I take the more interesting points of confusion and I show those the next day in the class and turn them into questions. So the students very quickly discover if I take the effort of communicating to Professor Mazur what is confusing, there's a good chance that we'll either go over it in class or he will address it via an email. And that turns out to be quite a large incentive for the students to stay on top and to to give me meaningful feedback that I can actually use. Yes?
I don't teach, but I have students who work for me, and one of the things they complain about a lot is clickers not being used the way they should be, so they can learn to use. Just talking about, big clicker revolution now. Do you think that that's a problem universally, that, they're using it, but, attendance or...
Yes, so the question is about the use of the clickers and some students complaining about them being misused. Notice that I downplayed the clickers completely. In fact, to me, what matters is the pedagogy. You don't need clickers. We're equipped with perfect devices called hands, and whenever I give a workshop on clickers, I show that they're not necessary. I start with clickers, and then I have students, the audience, professors, not students, put their hands on their chest and use fingers to indicate their choices, right? So you can just use that. And I used to get really annoyed at people who say, oh, I've adopted your clicker technology. Well, it's not my clicker technology. It's the pedagogy that matters. I've discovered, meanwhile, that a lot of people who start using clickers then eventually discover that you have to have a pedagogy behind it. But yes, unfortunately, there are some people who are using the clickers incorrectly. For example, I've noticed some people who say, oh, I'm using your clickers in peer instruction, and then I listen to their description, and all they're doing is they're lecturing like they always would, and then they stop, they ask a question, they have the students press a button, and then they say, this is right or this is wrong, and go on. So they're literally taking the peer out of peer instruction, right? You need to have the commitment, the individual commitment, so you have to give the students an opportunity to think, commit themselves, then argue verbally among themselves, and then vote again. That's, in my opinion, the only correct. There's a lot of data. The University of Strathclyde at Glasgow published an interesting paper where they used two different modalities. One was they posed a question, and then immediately had students talk to each other and then use the clicker. And the other one was they posed a question, had the student think and click, and then talk, and then click again. And they showed two things. One is much more student satisfaction when the students got an opportunity to think before talking to somebody else, and also larger learning goals. So I think the data backs it up. There's another paper in the American Journal of Physics by Henderson that shows that a lot of instructors claim to use peer instruction and clickers, but they basically use them as a polling tool. Which of the following is not a living being? A fish, a rock, a butterfly. Press B. Well, that's not mentally engaging, right? It's like recalling of a fact. So I think that the technology per se doesn't do anything. And that's true for something probably to keep in mind as you evaluate the technologies in the next day and a half. Technology by itself doesn't do anything. And technology in education in particular is only good when it allows us to do something we cannot do through other means. So taking something that you can do perfectly well and transferring it to some new technology won't afford any new modes of learning. For example, taking your lecture notes and putting them into PowerPoint won't make it go faster into the brains of the students. That's an extreme example here. Asking a question is just a polling question where you have students press, fish, rock, butterfly. That's not very good either. But if you find a way of engaging the students in the classroom through technology, that's great. Now, you can engage them by just using hands on the chest. But the great thing about the technology is that you keep a record which then allows you to determine which questions work best in your setting. So you can become more rigorous about selecting good questions for your audience. Thank you for asking that question. Let's take one more. Yes?
Have you tried this with a mixed class where some of them attend the lecture and some of them remotely attending the lecture? And has that reduced the effectiveness because they can't discuss with each other as well?
Very good question. So have I used this with in settings where part of the audience was in the same space as I was and part was remote? I have. In fact, last semester I taught a course in South Africa, even though I've never been in South Africa, and I did that over Illuminate. The course was actually on interactive teaching, but I thought, you know, in order to teach an effective course on interactive teaching, you better use interactive teaching. Now, these were instructors who were at a lot of different campuses, Pretoria, Johannesburg, Cape Town, and so on, and lots of places I'd never heard of in South Africa. So actually there was no live audience at all, except for a few technical people who were sitting with me, helping me out. In the larger campuses like Pretoria, there were 20 people in one room. So there I could ask the people in the Pretoria room to talk to each other. But then there were a couple of campuses where there was only an individual. And you know, when you say talk to your neighbor, there is no neighbor. So what we did is we actually took all of the people who were sitting alone at their computers and paired them up with another person who was sitting alone at their computer and used chat. And Illuminate has actually a very nice feature where you can see a little balloon and it intensifies in colors as the people chat with each other. So here I was halfway around the globe and I said turn to your neighbor. I could even see the people who were sitting alone type away and chat with somebody somewhere else. It's just fantastic to see how you can engage people, you know, at a distance using this approach. Any other burning questions? Usually people always ask me, what happened to your evaluations? What happened to your evaluations? That's a burning question that everybody has. Well, the evaluation didn't change because, you know, it probably measures personality or something else. One thing has changed, however. I do not have a single student who writes Professor Mazur is lecturing from his lecture notes anymore. I took care of that. It's been replaced with something else, though. Now they write, some of them, Professor Mazur is not teaching us anything. We have to learn it all ourselves. Thank you.